Okay, welcome year 10, and this is lesson 2. So figure 1 shows 4 blocks of different materials floating on water. The blocks are the same volume. You can see here some are floating in the water and some are out. Which of the blocks has the smallest weight? Well, clearly it's the one that's floating on the water, and therefore the smallest weight has to be C. And figure 2 shows a life buoy next to a deep swimming pool. Life buoy figure 2. So I thought we were studying their diagrams to see what it is they're trying to get at. And over the page it then says the life buoy has a mass 2.5 kilograms, gravitational field strength 9.8 newtons per kilogram. Calculate the weight of the life buoy using this equation. Weight is mass times gravitational field strength. And so using the equation they've given us there, because weight is a force, remember, this is the same as this is, in case you're wondering, this is Newton's second law. It's F equals ma is exactly the same equation. So here, I've got to work out the weight, this one here. I'm given the mass, so, and I write here, weight equals, and another way I'm doing it, several of you would simply write down scribble numbers. It looks like a child of 3 has been just let loose on the page. You formally write it out like that, and then get your trusted calculator and do your 2.5 times 9.8. And I'm actually going right through this with you, 24.5, just to prove where these things come from. And put the answer down there. And again, several of you again will do your answering up here somewhere with lots of scribbling out and changes of mind, and then you never put the answer down here. Help the examiner to give you the marks. When thrown into the water, so we come to the next one, the life buoy floats. The two forces acting on the life buoy are the weight of the life buoy downwards and the upthrust upwards. How big is the upthrust on the life buoy compared to the weight of the life buoy? Tick one box only. Now, this is like the lesson where I put a stool on the table and said the stool's not moving. Here's my cup of tea. It sits on the table. The force pushing up on it must be the same as the force acting down on the table. They must cancel out. If they didn't, it would either go up or down. So the answer here, the upthrust, is the same as the weight. It floats on the water. It doesn't come out of the water, nor does it sink in the water. It then finishes off by writing down the equation linking acceleration, mass and resultant force. But it's the one that I put up here a minute ago. It's this one here. Newton's second law. You expected to know this. So force equals mass times acceleration, or F equals ma. And you have to know that. That's a must learn equation. Comes up a lot. So on to part E. We have a rope is used to pull the life buoy to the side of the swimming pool. Resultant force of 4 acts on the life buoy. The mass of the life buoy is 2.5. Calculate acceleration. So I would always write down the equation again. Always. There may be some marks in that, even if what happens next goes wrong. The force is 4. So 4 equals 2.5 times acceleration. I've got to get the 2.5 out of the way. I've said to you repeatedly, time and time again, the simplest way to visualise this is 2 crossed arrows going through the equal sign. And that's what this means is that if it's on the top, it goes down below, and if it's below, it goes on top as it crosses the equal sign. So let's do that. These are all on the top. So here my 4 equals 2.5 times A. 2.5's got to go, so it goes downwards. So if we come back up here then to set this out properly, I then have 4 divided by 2.5 equals A. It goes down. I now calculate that answer out for myself. So I go to my calculator and 4 divided by 2.5, make sure I've got the right way around, is 1.6. Simples. You understand? Easy. The only part in that you had to really worry about was rearranging the equation, which is the thing in physics. You can do that. Yeah, you're there. Interesting question, this one. The trolley is attached to 2 identical springs. The trolley is pushed to the left and then released. So it's going to go like this. Figure 1 shows the horizontal forces acting on the trolley just after its release. 1.5 there, 2.7. Now I'm actually watching these to make sure they've not changed any of the units. Write the equation linking acceleration, mass and resultant force. So just as before, force, you see that, equals mass times acceleration. On to part B. So on part B, the trolley has a mass of 0.75 kilograms. So calculate the acceleration of the trolley to start, which at least give the unit. Now this is worth 4 marks. I hope you can see that. There's a bit more to this than meets the eye. And so we start off with our equation, F equals ma. After all, they were trying to lead us into it just here. So let's put our numbers in. What's the force? Well, if you go back to our diagram, and we look very carefully, there's 1.5 pulling that way, and there's 2.7 pulling that way. It's two forces opposing each other. So the resultant force, the total force acting on that trolley, will be 2.7 take away the 1.5. It's like a tug of war on the playground. It's just one side's pulling harder than the other. So that's going to be the force we're going to have to use. So we have 2.7 minus 1.5. I'm going to put that in brackets a minute, equals the mass is 0.75 times acceleration. Okay, so 2.7 take away 1.5 should give us 1.2 equals 0.75 times A. So now I've got to rearrange the equation. It's exactly the same one as before. I'll do it all over again. Remember this rule. Either side, you go crisscross across. It's at the top, it goes down. So we have 1.2 divided by 0.75 equals A. So let's do that. 1.2 divided by 0.75 equals 1.6. As 1.6 is acceleration. Units, you should know this. Well, what we were measuring in was meters and seconds, so it's meters per second squared. You can do it that way, and you can also go meters per second per second. Either one of these is correct. Now the next part of the question is a little bit unfair because you've not covered this work exactly, and I'm going to refer you here to a page in the textbook in case you want to look this up. You're going to have to come across this work soon, and this is waves. It's chapter 12, it's the start of chapter 12, and it's on page 175 of the textbook, transverse waves. And transverse waves, oscillations of a transverse wave are perpendicular to the direction in which the wave transfers energy. Sounds like gobbledygook until you come to this question. When the trolley is pushed and released, a wave travels along the cord. So it's going to go like this way. It's going to pull the cord this back and forth like this. What type of wave travels along the cord? And the answer is transverse, because it's at right angles to the force. And so the answer is because it is at right angles to the force. The other word for right angles we could have used the word perpendicular. We could also use that. But that would give me the marks of the question. Easy marks to get there. But it requires part of another chapter of the book. To be fair to you, we haven't yet gone to that, but I can't always break the questions up into these convenient sections. So then we have this. Suggest one change that could be made to the apparatus shown in figure 2 to produce a wave with a lower frequency. And the obvious thing then to make a change would be to make it go faster or slower. So a lower frequency means it's going fewer cycles per second, so we can pull less far on the trolley to start. Or we could weaken the springs. Okay. The next one's a classic experiment. We might have done it in biology. Certainly would have done it with me at some point in the past. The figure below shows two students investigating reaction time. And they're going to drop a ruler and catch it. Student A lets the ruler go. Student B closes her hand the moment she sees the ruler fall. Investigation can be used to find out if listening to music changes reaction times with students and how, and it is for a glorious 4 marks. And the sort of thinking that you're going to do here, you're going to measure the distance the ruler falls. The greater the distance, the greater the reaction time. Whoops. Greater the distance, the greater the reaction time. I was getting ahead of myself there. And I've done classic thing here. Always tell you not to scribble out like this. I'm actually doing it for the camera's benefit. If you're going to cross a word out normally, put a straight line through it. And repeat the measurements more than once. This is my best handwriting here, children. If you've got rubbish handwriting like mine, just make it large. At least it looks rubbish large. And then repeat measurements more than once. Repeat listening to music. Because I'm doing this live to the camera, I'm not going to put all the bits and pieces in. Calculate a mean would be an obvious thing to do. And compare the means. Is the difference significant? This experiment is a useful one for you to do because it comes up in physics and it comes up in biology as set practicals. It's the same practical. So, a second group of students used a stop clock and computer simulation test to measure reaction time. This table shows the results. And you can see across the lines here, well, you've already looked at it, I hope, there's a difference. One conclusion can be made from the results for students X and Y. Well, as you can see, X and Y, as they go along, they get faster. So as they repeat, they get faster, which is quite normal for this experiment. Student Z gave an anomalous result, particularly at the end there. So just 2 possible reasons why that occurred. Well, the student could have been distracted, because obviously this is an experiment on a human being. The second thing, the stop clock was started or stopped incorrectly. So the stop clock itself is not incorrect. The stop clock is incorrectly used. And that gets you full marks for that. Okay, thank you.